Hi everyone, welcome to our first week of MATH-170, where we'll start extrapolating from our data and looking at some types of regression, namely linear, quadratic, and exponential. So we'll start with some definitions, and the idea of doing regression is to make predictions based on something. And so the variables that we actually measure and that will serve as predictors for a certain behavior, a certain outcome, are called independent variables. The variables that we are trying to predict are the dependent variables. And usually we work with one or more independent variables to conclude of one dependent variable, which we also call outcome. So the definition of dependent variable is the variable that is being modeled as a function of the independent variables. And as I mentioned, the goal is to approximate with as much precision as possible the value of the independent variable for all possible values of the dependent variables. And so this process of finding the function that better predicts the outcome uh, based on the values of the independent variables is what we call regression. Let's look at one example of how this can be used in everyday life. So we have some data here regarding a certain number of weeks of hours of support in a week um, as a function of the number of clients that a certain company has, or maybe this is we have a group of companies that we provide support to, and the number of clients that each company has, and how many. As a let me Doesn't make any difference for our exercise, but here I say monthly, so I'm going to say monthly here too, makes no difference. Um, so the number of monthly hours of support and here too, trying to predict monthly. So knowing that for our client, that the company that has 1,862 clients, there were 33,186 hours of support, and for a company with 2,122 clients, there were 40,976 hours of support, and so on. We try to predict how many hours of support will be needed. For instance, if there are 2,700 clients in a company. So that's the type of exercise that we'll be trying to do our best estimate for this situation. There are several types of regression. One of them is the linear regression, where we try to fit our data into a function that is a straight line. It can be a growing straight line or a decreasing straight line, but it's going to be a straight line, and being a straight line, the regression function is going to be of the type y equals a times x plus b. A is the slope, the angle that this line makes with the x-axis, this angle here, and b is also called the linear coefficient, and is the value that y has when x is 0. For instance, how many hours of support we would have with a company with no clients. And in some situations, y is going to be 0 when x is 0, and other situations it's going to be different. And this is when it's not always possible to use a straight line. And the problem with straight lines, even when it is possible, is that this type of regression is very susceptible to outliers, which means that it's not adequate for big data, because in situations of big data we often have many outliers. And I'll just show an example of how that gets affected. So looking at this data has exactly the same data points, with the exception of one, which is this one here. Let me do it a little bit better. This one here was up here. It's the same. I just changed this. Let me having a little bit of technical problems here with the. So this one here, in this second chart, the measurement was made down here, and so somewhere around 3700, if we only had kind of 11,000 here, while in this situation we had 80,000. All the other points are the same, and you can see here that the line is not very far from any of these points. But the simple fact that we had one situation that was either exceptional or we made a mistake when measuring it, and that brought us to here, shifted the line, and now we have several points here that are quite far away from the line, because this line kind of gets attracted to this point. And so it's very susceptible to outliers, and outliers can happen due to exceptional situations that occurred when we were collecting the data, or due to failures in measurement, which can happen due to a failure in the mechanism of measuring, like a machine that is doing the measurement and has a problem in one of the measurements, or due to errors in when somebody is inserting the data. And if we have millions of data points, like it happens in big data, just think of all the electrical power consumption of metropolitan city. It's millions of data points, and a few errors will make a big change in a linear regression. When you do a linear regression, and we will see how to do this, and how to calculate these equations in an easy way using tools. The idea is to use that regression to predict outcomes. And so we have, in this case, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 data points. And now let's go back to our initial question, and just what happens if we have 2,700 clients. And so the goal, and notice that I came back to the situation where I didn't change that outlier, so that we have something that is, actually this is a different set. So if we have 2,700 and we did this linear regression, the software is going to tell us the equation. In this case, the equation is y equals 19,004 times x plus 1,606, sorry, 19.004 x times x plus 1,660.5. And so if we have, if our data is, what was it again, 2,400? 2,700. So if you are trying to estimate what's going to happen when the number of clients, x, is 2,700, again, catching a line there, I don't know what's going on. Let me pause for a second and clean my path. Let me see if I can do it now with no problems. So I want to know x with 2700, y, which is the estimate for the number of hours, it's going to be 19.004 times 2700 plus 1660.5. Okay, I'm going to do this neglecting that point of 0.004, and I'm going to do times 19, just rounding this down to 19. 63, 18 plus 6, 24. 24, and then we have plus the 1006.5, and so something like 52,960.5 hours for this situation, which would place us something like around here, which makes sense because 2700 is also somewhere here. So this makes sounds about right.